Welcome to today's lesson where we will be looking at balancing redox reactions. Balancing redox reactions has two fundamental steps, balancing the electrons and balancing the number of atoms. As a quick refresher on what redox is, it is essentially two half reactions, in which one is losing electrons and the other is gaining electrons. We can understand redox reactions by analyzing the name. The RED portion of redox, or red, stands for reduction. This is a half reaction in which electrons are gained and the species becomes more negative. The OX stands for oxidation, where the species loses electrons and is said to become more positive. So going back to balancing, redox reactions can be balanced using two methods. One is the oxidation number method and the other is the ion-electron method. We will be exploring both of these methods with different examples in the upcoming segments. Okay, this is the first redox example that we will be looking at, and we are going to be balancing this through oxidation number method. So the first step of this method is to determine the oxidation numbers of everything in this redox reaction. So to do this, you must have your rules memorized, and I won't be going over all of the rules, but the ones that are relevant to this example I will be discussing. So phosphorus exists as its own, as an element, and so it gets an oxidation number of 0. For any neutral compound, the sum of the oxidation numbers must be equal to 0. And we know that oxygen has the oxidation number of -2 unless it's a peroxide or it's bonded to a fluorine. Since we don't have either of those scenarios in this water molecule, we will assign a -2 oxidation number. The hydrogen has a charge of +1 unless it's in a metal hydride. Since this is not a metal hydride, it gets the +1. Now we can check because +1 times 2 is +2, which cancels out the -2, giving us a sum of 0. So here again, the oxygen gets -2, the hydrogen gets a +1, so we have -6 and 1, -5. Therefore, the nitrogen has to be a +5 in order to make the sum 0. Here, oxygen again gets a -2. Hydrogen gets a +1, -8, +3, -5. To balance out the -5, phosphorus therefore has a charge of +5. Sorry, not a charge, an oxidation number of +5. In nitrogen monoxide, oxygen has an oxidation number of -2. Nitrogen, therefore, must be +2. And that is how we determine our oxidation numbers. Okay, now that we've figured out the oxidation numbers, we can move on to step 2 of balancing, which is to identify the oxidation half reaction and the reduction half reaction. So basically, we want to know which species is gaining electrons and which one is losing electrons. So to do that, we analyze the oxidation numbers. So we immediately see that phosphorus goes from an oxidation number of 0 to +5. It's becoming more positive, and so it must be losing electrons. To go from 0 to 5, it must have lose 5 electrons, making this our oxidation reaction. So because it's not in a 1-to-1 ratio, notice how this has a subscript of 4 and this 1. So we have to multiply this by 4 to get the total number of electrons being lost, which is 20. So the 4 here becomes important when we start to balance the reaction. It's our first multiplier. So I'll actually put a box around that so we keep that in mind for later. Moving on to the reduction portion, this is the species that is gaining electrons or becoming more negative. So if we look here, we see that nitrogen goes from +5 to +2, becoming less positive or more negative, and so it is obviously gaining electrons. How much exactly? Well, +5 to +2, it is gaining 3 electrons. It's in a 1-to-1 ratio, so we don't have to worry about multiplying or adding any extra multipliers. If you want, you could put the 1, so we have 3 electrons, and that's our reduction reaction. And so there we've identified the reduction and the oxidation portion. Okay, our next step is to find the LCM of electrons gained and electrons lost. Why do we do this? Because the whole point of balancing is to balance not only the atoms but also the electrons, right? So as we can see, the electrons are not balanced right now. We're losing 20 and we're gaining 3. There's a difference of 17 electrons. So in order to balance the electrons lost and gained, aka balancing the electrons in general, we will be finding the LCM. So between 20 and 3, the LCM is 60. So to get 60 from 20, we will be multiplying it by 3. So notice in this line, this is actually our second multiplier. I'll circle that. And then in this line, 3 times 20 gives us 60 electrons. I'll multiply this. This is our only multiplier in this line. So now we are losing 60 electrons and we're gaining 60 electrons. So it balances out. We're losing the same amount as we're gaining, so basically the difference is 0. It's balanced, right? So now that we've done that, we can actually add in the coefficients that balance out this reaction. So with the phosphorus, we have 2 multipliers, 4 and 12. Because this phosphorus already has the 4, we only need to add in the 3. So now on our reactant side, we have 12 phosphorus, which means naturally you'll think that on this side we must also need 12. We can come to that conclusion by looking at our multipliers. Since this was lacking a 4, we need to add in a 4 here, but also the 3. 4 times 3 is 12, so we'll just add in the 12 right away. Moving on to the nitrogen, there's only one multiplier, which is 20. So we add 20 here, 20 nitrogen, we need 20 nitrogen there. So yeah, we are adding the same multiplier to both sides. So now our atoms that are not hydrogen or oxygen are balanced. 12 phosphorus, 20 nitrogen, 20 nitrogen. In the next step, we will look to see if the oxygen and hydrogens are also balanced. So now in our next step, we're going to be checking if the hydrogens and the oxygens also balance out. So we'll just count. Here we have 20 times 3, 60, 61 oxygens. Here we have 12 times 4, 48, plus 20, 68 oxygens. So 68 versus 61, we're lacking 7 on this side. So what we can do is we can add in a coefficient of 8 here to get 20 times 3, 60, plus 8, 68. So we'll do that, 8, and hopefully this automatically balances our oxygen as well. So let's check. 20 plus 16 is 36. 12 times 3 is 36. So as we can see, we have our oxygens balanced and our hydrogens balanced, and so this is our final answer. I'll rewrite it to show without all the chicken scratch on the side. So our final answer is 3 phosphorus plus 8 water plus 20 nitric acid plus 12 phosphoric acid plus 20 nitrogen monoxide. And we are now done with this example. We are done with oxidation method. We'll move on to ion-electron method, and we'll show 2 examples for that. So when it comes to balancing redox reactions using ion-electron method, there's a little catch because the steps are actually a little bit different based on if the redox reaction occurs in a neutral or acidic solution versus a basic solution. So we'll be covering both examples, but first we'll be discussing acidic solution redox reactions. For this, we will be using this example. And so step 1 when it comes to balancing with ion-electron method is to split the reaction, the full redox reactions, into 2 half reactions, because we know that a redox reaction really is just that, 2 half reactions. So when it comes to oxidation method, we know to split it between the redox reaction, the reduction reaction, and the oxidation. Here we'll just split it intuitively based on what the reactant turns into as a product. So you can tell that the arsenic oxide will become the arsenic acid, and the nitrate ion will become the dinitrogen trioxide. It wouldn't make sense for this to become that and this to become that, right? So it's just intuitive. So here we have our half reactions, And then the second step, which I already started to do, is to balance all atoms that are not hydrogen or oxygen. So in this first half reaction, we see that there's 2 arsenics, and here we only had 1, right, from the original. So I added a coefficient of 2 to balance that out. In the second half reaction, we had nitrate, and then which became dinitrogen trioxide. So since there's 2 here and 1 here, I added a coefficient of 2. So now comes the fun part where we balance the oxygen, hydrogen, and charges. So to do that, we take out our component table. So you should make a small one of this each time you solve one of these problems, just on the side to know what things to add. So we look at this and we see that for every oxygen that we need, we will add 1 H2O molecule. That's on the side that's deficient of the oxygen. For every hydrogen that we need, we'll add in a hydrogen ion, and for every electron that we need, we'll add an electron to the more positive side. That's how we balance out the charges. If one side is more positive and one side's more negative, we can't add protons. We'll add electrons to the more positive side, making it equally negative. Okay, so I'll keep that right here. We don't need the original one anymore. We'll work with this. So, water, oxygen. We'll look at the first half reaction. We see that we have 2 times 4, 8 oxygens and 3 oxygens. So that's why it's important to balance out the non-hydrogen oxygen atoms first, because if we didn't add this 2, you would think that there is 4 oxygens, but no, there is 8. So we'll add 5, we need 5 oxygens, so we'll add 5 water molecules, plus 5 H2O. So when we add a water molecule, we're also adding these hydrogens, right? So now we'll look to see if the hydrogens are balanced. We have 2 times 3, which is 6 hydrogens, 5 times 2, which is 10. So we need 3 more hydrogens on 10, 6, 4. We need 4 more hydrogens on this side. So I'll use my green pen for that, just to color coordinate with the component table. So plus 4. Okay, and now we're done with the oxygens and hydrogens, so we'll look back to our charges. The reactant side has a charge of 0. There's no ions. Here we have a charge of plus 4. So we're adding electrons to the more positive side, which is the product side in this example. So we'll add 4 electrons, right? 4 electrons. So that makes our charge 0 and 0. So now for the second half reaction, there are 6 oxygens, 3 oxygens. So we'll add 3 H2Os, right? Because we need 3 more oxygens. And in that process, we accumulated 6 hydrogens. So we'll add 6 hydrogens to this side to balance that out. Hydrogen ions, so there's a charge. So now we'll balance the charges. The nitrate has a charge of 2 negative. And then there's 6 positive here, making the overall 4 positive. Here the charge is 0, so we need to add 4 electrons to get the 4 positive charge to be neutral. So now what we do is we can cancel out anything that exists on opposite sides and add what is in common on the same side. So to know if you did this right, the electrons must always cancel out. We shouldn't have any electrons left over in our final answer. So the 4 electrons here, 4 electrons here, they cancel out perfectly. Now in some examples you might have to find the lowest common multiple so that the electrons will cancel out, but they always have to be on opposite sides or else they won't cancel out. So now let's look to see if anything else cancels out. We have 4 hydrogen ions, which cancels out with the 6 here. So the 6 will become a 2. We have 5 H2Os and 3 H2Os. This will cancel out and we'll get 2 H2Os here. The 2 NO3, yeah, nothing else cancels out, so we can start to write our final answer. So in our final answer, we'll have A S2O3 plus 2 nitrates plus 2 water molecules plus 2 hydrogen ions yields 2 H3ASO4 plus 1 N2O3. That is our final answer. Now to check, we can make sure that our charges and our atoms are all balanced. So we'll just do our count. We have 2 arsenics, so that's good. We have 2 nitrogens, that's good. We have 3 plus 6 plus 2, so 6, 9, 10, 11 oxygens. We have 4 times 2, 8, plus 3, so 11 oxygens. We have 4, 5, 6 hydrogens, 2 times 3, 6 hydrogens. Now let's check our charges. We have 2 negative, 2 positive, giving us a charge of 0, and a charge of 0. So this is our final balanced answer using ion-electron method. And keep in mind, this is an acidic solution. So the only real change between an acidic solution and a basic solution is this component table. So in our next example, we will be looking at a basic solution, a redox reaction in a basic solution, and see how this is different. Okay, now for our last example of this video, we will look at a redox reaction that occurs in a basic solution. So for this, we will look at this example, and it's the same steps until you hit the component chart. So our first step will be splitting it into 2 half reactions. Our second step will be balancing all atoms that are not hydrogen or oxygens. So this may look different because there's only one reactant, which becomes 2 products. So you might think, how did that 1 nitrogen turn into 2 nitrogens? Well, keep in mind, right, this is not balanced. This is an unbalanced reaction. So there can be multiple nitrogens here. We haven't determined the coefficients yet. So when we split it into half reactions, the first one will be NO2 becoming a nitrate ion, and the second one is NO2 becoming a nitrite ion. So now we've done step number 1, very simple. Step number 2 is to balance all atoms that are not hydrogen or oxygen. So let's do that. There's 1 nitrogen here, 1 nitrogen here, 1 nitrogen here, 1 nitrogen here. Okay, easy. We didn't have to do anything. It was already balanced. So now we come to our component table. And this is what sets apart the basic and the acidic solutions. So we notice here the table already looks very different because there's 2 molecules in the how section of the table. So what that means is for every oxygen that you need, you will add 2 hydroxide ions to the side that's deficient and 1 H2O on the opposite side. For every hydrogen, you will add 1 H2O on the side that is deficient and an hydroxide ion on the opposite side. But the electron part stays the same. You simply add electrons to the side that is more positive to get the charges to be equal to each other. Okay, so now let's start balancing the oxygen, hydrogen, and charges. Oxygen. There's 2 oxygens here, 3 oxygens here. We need 1 more oxygen on this side. So what we do, we add 2 hydroxide ions for each oxygen we are deficient in. We are deficient in 1 oxygen, so we will add in 2 hydroxide ions. So again, I left a lot of space because we're going to be adding components, right? So because we added 2 OH negative, we are not done yet because we haven't done this step. We need to add in a H2O on the opposite side. So 2 hydrogens, that's balanced out. 4 oxygens, that's balanced out. Now charges. The reactant side has a charge of 2 negative, 1 negative here. This is more negative, this is less negative. So let's add an electron to make this side equally negative. Now we can move on to our second half reaction. Again, the N's were balanced out. The O's are even balanced out. So we just need to balance out the charge. This side is negative, this side is neutral. So let's make this side a bit more negative so that they are equal in charge. Now we simply cancel out everything that can be canceled out and combine things that can be combined to get our final answer. So again, the main point is to cancel out the electrons. That's how you know if you've done it right. So because we have the same number of electrons on opposite sides, we don't have to multiply the reactions by an LCM. We will just cancel out. And nothing else actually cancels out. So we can combine anything that can be combined. So we see here the NO2 and the NO2. They combine. 1 plus 1, 2. 2 NO2 plus 2 hydroxides yields nitrate and a water molecule and a nitrite ion. So this is our final answer. Let's check if we did it right by counting the atoms and the charges. So we have 2 nitrogens here. 1, 2 nitrogens here. We have 4 plus 2, 6 oxygens. 3, 2, 1, 6 oxygens. We have 2 hydrogens. We have 2 hydrogens. Okay, perfect so far. Now let's check the charges. We have 2 negative. A charge of 2 negative on the left side. Negative, negative, 2 negative on the right side. So this is our final answer and we are done. So again, exact same as balancing a redox reaction in an acidic solution, except this component table. So you will be able to balance redox reactions using ion-electron method as long as you have these 2 component tables memorized. So that concludes our lesson for today. I hope you understand how to balance using oxidation method and ion-electron method. That concludes balancing redox reactions. Thank you for listening.